Hi, in this video, I want to introduce to you the fundamentals and climate change impacts on the Salish Sea. But why the Salish Sea? In fact, the Salish Sea is not known by many people, although it is one of the world's largest and biologically rich inland seas. Even for those people in Washington and British Columbia who live alongside it, less than half of them have heard of the Salish Sea. According to a report from Sea Doc Society, only 5% of Washington people and 14% of BC people surveyed can identify the Salish Sea. So why is it called the Salish Sea, and where exactly is it? Its name pays tribute to the first inhabitants of the region, the Coast Salish. The Salish Sea is a marine ecosystem that spans the United States-Canada border and includes both Seattle and Vancouver. The Salish Sea is about 440 kilometers long and has a surface area of about 18,000 square kilometers, which is roughly the same size as the Gulf of Riga in northern Europe. This combines the total surface area of the Strait of Georgia, Strait of Juan de Fuca, Puget Sound, and various other bodies of water. The sea has an average depth of 130 meters and reaches a maximum depth of 670 meters. Thanks to the complex shape of the Salish Sea, it is framed by more than 9,400 kilometers of shoreline, including the mainland and island shores. Here is a graph of the major rivers connected to the Salish Sea. Approximately 45 watersheds together with several major rivers freshen the Salish Sea. The Fraser River is a dominant source of freshwater and sedimentary particles, contributing approximately 50% of the freshwater entering the Salish Sea system. Other freshwater sources are also important in terms of bringing sediment and freshwater to their deltas and estuarine wetlands. The combination of freshwater input from the watersheds and Pacific Ocean-derived marine waters give the Salish Sea its unique oceanography and ecology. The Strait of Juan de Fuca is the main connection of the Salish Sea to the Pacific Ocean, with a smaller connection at the north end of the Strait of Georgia through Johnstone Strait. There are two primary basins, the Strait of Georgia and Puget Sound. However, a series of sails divided the Salish Sea into subbasins. These submarine ridges are also important bathymetric features and geospatial reference points due to their influence on the circulation of water. So what is the circulation like in the Salish Sea? The circulation patterns in the sail basin system of the Salish Sea are estuary-like. Large amounts of fresh water enter at the surface through rivers in the Puget Sound and Strait of Georgia, especially the Fraser River. A multi-layer flow is driven, with fresh water flowing westwards towards the Pacific Ocean and the denser Pacific Ocean waters flowing east into the Salish Sea. This is known as estuarine exchange flow. The deep saline inflow from the Pacific Ocean travels through the Strait of Juan de Fuca and over a series of shallow sails where it mixes with the overlying fresh surface water traveling seawards. Mixing is modulated by tidal currents, creating turbulent mixing in a mid-layer and results from the spring and neap tidal cycle on short time scales, with higher mixing rates during the spring tides when tidal currents are stronger. The transport of ocean water into and fresh water out of the Salish Sea decreases the residence time of waters within this inland body of water. For example, in Puget Sound, residence time is approximately 5 years based on river flow alone. However, the estimated residence time is dramatically reduced to 90 days to 180 days after accounting for the exchange flow. Globally, increasing greenhouse gas emissions and the resulting increases in concentrations of CO2, CH4, and NO2 are driving changes to the Earth system, referred to as climate change. Their impacts alter much more than just temperature in the marine environment by affecting ocean currents, salinity, water density, pH level, and other structural elements of marine system. Of course, the Salish Sea included. Since 1900, air temperatures on Earth have increased by about 0.75 degrees Celsius and by nearly 1.1 degree in the Pacific Northwest. The Salish Sea region has shown a warming trend starting from around 1980. The Salish Sea model presented here is a complex hydrodynamic model developed for the Salish Sea and serves as a tool with which to assess changes in Salish Sea conditions. As part of a recent study by Amos and their team, their model showed a projected increase in sea surface temperature of 2.6 degrees by the end of the century. Mixing and circulation driven by ocean water mediate some of the temperature caused by increasing air temperature and temperatures of inflowing freshwater. However, the mediating properties may diminish as the ocean warms. The rising temperature has significant impact on the distribution of precipitation. Historically, rainfall and snowfall contribute to total precipitation relatively balanced, while in the future, more areas will become rain-dominant. Snowfall is expected to decline as temperature warms, and will be replaced with rain events in the mountains, which will result in increased winter streamflow, as snowpack typically serves as a water reservoir to hold fresh water until seasonal temperatures are warm enough to begin seasonal freshwater delivery melting. This is crucial to freshwater delivery of the Salish Sea, because snow and ice serve as hydrological stabilizers, reducing variation in freshwater flow from the mountains to the coast. Water delivery will increase throughout the winter season, but will be seasonally reduced during the spring meltoff. This change will likely have significant implications for estuaries, leading to changes in circulation and transport of nutrients, oxygen, sediment, and biota. Aside from increasing temperature, ocean acidity is being predicted to continue increase for the next century. Ocean acidification refers to the chemical changes in the ocean caused by absorption of CO2 from the atmosphere. Since the beginning of Industrial Revolution, when carbon emissions began to increase significantly, the global average pH of surface ocean waters has declined by 0.1 pH units, which is approximately 30% increase in acidity. Ocean acidification currently plays a small but significant role in reducing the pH level of Salish Sea waters, and is somewhat seasonally driven. The data here shows a seasonal pattern to pH level, which more acidified water presents in the winter months compared with the summer months. This seasonal pattern is driven in part by phytoplankton production taking up CO2 and thereby modulating pH during the summer months. Khangaonkar and their team studied the changes in pH in the future with a Salish Sea model. The model results show that in the future year 2095 scenario, primarily driven by the global acidification effects in the Pacific Ocean, most water of the continental shelf will be at lower pH levels, with maximum acidification near the entrance predicted at -0.3 to -0.4 units. Accompanying ocean acidification, predicted dissolved oxygen level is also reducing. The regions of hypoxia and lower pH waters are found to occur in the same poorly flushed subbasins, such as Lynch Cove in Hood Canal. Rising sea level is not to be neglected. Globally, sea level has risen about 20 centimeters on average over the past century. As for the Salish Sea, RSLR is expected to exceed 15 centimeters by 2050 and 45 centimeters by the end of the century. The combining forces of climate change will cause many impacts on not only the marine system but also the human society. For more than 10,000 years, indigenous people have lived along the shores of and cared for the Salish Sea. Today, the region is home to almost 9 million people, and that number is rapidly growing. The Salish Sea is under relentless pressure from an accelerating convergence of global and local environmental stressors. Some of these impacts are well understood, but many remain unknown or difficult to predict. Restoring the Salish Sea and supporting its resilience are urgently necessary in years ahead. Thanks for listening, and that's all for my presentation.